Bismillah ar-Rahman ar-Rahim. This is lecture 2 of electromagnetics 1, and it's a bit long, and it's about the method of images. We'll start with the simplest problem of a point charge above a conducting ground plane. And we know from the uniqueness theorem for Laplace's equation that if a solution satisfies the boundary conditions, then it is the only solution. Here we guess at the solution, building on our knowledge of images in mirrors. So for a point charge plus q at 0, 0h, above a conducting ground plane at z equals 0, we postulate the existence of an image charge minus q at 0, 0 minus h, such that the electric potential V and electric field E in the region above the ground plane are found by superposition. And are 0 for z less than 0 inside the conductor in the ground plane. If the solution is correct, it must satisfy the boundary conditions, which are 1, V equals 0 at z equals 0, 2, E is perpendicular to the ground plane at z equals 0, and 3, that the total induced charge on the ground plane must equal minus q. Solution: V of r at any point above the ground plane is the potential from plus q plus the potential from minus q. R1 and R2 are the distances to the field point. Okay. At z equals 0, V of rho and phi equals 0. Okay, I'm using here polar coordinates or cylindrical coordinates because of the symmetry of the problem. The two charges are on the axis of a cylinder, you can imagine. Okay, and if we calculate based on this, the distances are R1 is the square root of rho square plus z minus h. So rho square stands for x square plus y square. Okay, and here we have cylindrical symmetry with respect to the axis, the z-axis. So it is independent of phi. So if we calculate the electric field, it's the minus gradient V. It has only two components, arrow and AZ, along arrow and along AZ. And these are given by these equations. You can work them out and check. Okay. Now at Z equals 0, E rho equals 0. It is the tangential component along the conductor. And it is obvious from these equations, you can see that E rho equals 0. And Ez is not 0, and it's equal to minus q times h over 2 pi epsilon naught times rho squared plus h squared power 3 halves. So E normal to the conducting ground plane as expected. Surface charge density is dn equal to epsilon naught Ez is equal to rho s. So the total induced charge, Q induced, is the integration of rho s over the infinite ground plane, which we take as an infinite circle. Okay, so integrate rho s ds, and ds is rho d phi. Okay, integration over phi gives 2 pi, and the integration over rho, you can see that the integrand is an exact differential. It's the derivative of 1 over the square root So the integral is just 1 over the square root. And if you evaluate between the limits from 0 to infinity, you get qh times 1 over h. So it is equal to minus q as expected. So q and its image are a solution to Laplace's equation. Well, next, let us take up the problem of images in spheres. Image in a sphere, and we will reach a relationship called inversion in a sphere. Suppose a point charge plus q is placed at a point distant r from the center of a conducting sphere, as shown in the figure. Okay. The sphere has radius a. As in convex mirrors, the image is smaller than the original, and its position r prime from the center of the sphere, taken as origin, is also unknown. So we have a problem in two unknowns, q prime and r prime. From symmetry of the problem, I will choose a representative cross-section of the sphere in the xy plane as shown below. Okay. Here the boundary conditions are v equals 0 at any point p on the surface of the sphere, and the tangential electric field E equals 0 at any point P also. So V at point P, a general point, is just Q over 4 pi epsilon naught R1 plus Q prime over 4 pi epsilon naught R2. R1 is just square root of R minus X square plus Y square, and R2 is square root of R prime minus X plus Y square. Choosing point P to be the point x equals 0 and y equals a on the y-axis. We could equally choose the point x equals a, y equals 0 on the x-axis on the surface of the sphere. We will get the same result. So we start with this for x0 and y equals a. You will see that q over 4 pi epsilon naught square root r square plus a square plus q prime over 4 pi epsilon naught r prime square plus a square square root equals 0, should be equal to 0. This is an equation. It has the two unknowns q prime and r prime, which we can simplify. Okay, this is equation 1. Then the tangential electric field is E phi here on the surface of the sphere, which is the dot product of E with A phi. And A phi is the unit vector minus sine phi AX plus cosine phi AY. At P 0A phi equals 90 degrees, so we only get the sine phi component, the x component. Okay, so we come up with this equation, which simplifies to equation 2. Now, if we divide equation 2 by 1, we get r over r square plus a square equal to r prime divided by a square plus r prime square. This equation is satisfied by r prime equal to a square over r, and you can check that. Substitute in the right hand side for r prime, and simplifying, you will find that you get r over a square plus r square equal to the left hand side. So it is checked. So this relationship is called inversion in a sphere. So r prime equals a square. And if we substitute into equation 1, we obtain q prime to be minus a times q over r. Since r is greater than a, so q prime is smaller than q. And you know this from spherical mirrors. If you have a convex mirror, the image is smaller than the original. So this solves Laplace's equation in view of the uniqueness theorem. Now we take up a more complicated example of the infinite two-wire transmission line. So let us consider two parallel lines of charge along direction of Z, which is perpendicular to the page here. They are separated by a distance 2s between them, plus rho L is at s and 0 in the xy plane, and minus rho L is at minus s 0. The y-axis is the reference for potential since it is equidistant from both lines, and the resultant electric field at any point 0y is perpendicular to the y-axis and directed along minus x. Okay. So the y-axis is an equipotential line. You can check this by taking a point on the y-axis and drawing the lines from plus rho L and minus rho L. Okay, and you will see that V equals 0 and that the electric field is perpendicular to the plane, which is in the direction from positive charge to negative charge in the direction of minus x. Okay, so now if we calculate the electric field, we know for a line charge plus rho L, E2 is rho L over 2 pi epsilon naught R2, as seen in the figure, okay, in the direction of A2, okay, direction of R2, which gives us V then, which is the integral with respect to R. It gives us the integration of rho L over 2 pi epsilon naught dr over R, which is ln R. And R, from the reference for potential, which is the y-axis, it is a distance s, okay, and R2, so it is the potential between the origin, let's say, and R2, the point P, okay. Also, V minus is the potential due to minus rho L, okay. It is likewise given by the same form of equation, rho L over 2 pi epsilon naught ln R1 over S, okay, because of the change of sign. Then if we add the two potentials, V equal to V plus plus V minus, we come up with VL equal to rho, V is equal to rho L over 2 pi epsilon naught ln R1 over R2. Okay, so if we substitute for R1 and R2, it is the square root of x plus s squared plus y squared for R1 and square root of x minus s squared plus y squared for R2. Well, this equation can be put in this form. Ln R1 over R2 is 2 pi epsilon naught times V over rho L. Taking the exponential, e to the power ln R1 over R2 is R1 over R2, and it is equal to the exponential of 2 pi epsilon V over rho L, which is a constant if we take V as a constant. Call this constant K. Here, if V is a constant, we have an equipotential surface from this equation. This is an equation in the xy plane. Okay, if you put V constant, so it becomes the equation of a surface, which is an equipotential surface. Okay, so if we solve this equation, okay, substituting for R1 and R2, okay, we rearrange as shown here, and we come up with this equation here. This equation looks like the equation of a circle. So if we complete the square for x, okay, by adding s times k squared plus 1 over k squared minus 1 squared to both sides, okay, rearranging terms, we come up with this, x minus h squared plus y squared equal to r squared. This is the equation of a circle, where h is the center, okay, on the x-axis, equal to s k squared plus 1 over k squared minus 1, and the radius of the circle r is 2ks over k squared minus 1. This circle is an equipotential line, which when extended in the z direction becomes the surface of a cylinder. It's an equipotential surface of a conducting cylinder. Now we come to inversion in a cylinder. If we imagine the circle of radius r is on the surface of a cylinder, a conducting cylinder, then plus rho L is the image of minus rho L outside the cylinder. If we measure the distances of plus rho L and minus rho L from the center of the circle, we find plus rho L is at a distance d1 equal to h minus s from the center, and minus rho L is at a distance d2 equal to h plus s from the center. If we take the product of these two distances, we get h minus s times h plus s is h squared minus s squared. Substituting from the expressions for h, okay, we find that h squared minus s squared is equal to r squared, which is d1 d2 equal to r squared. So compare this with r prime equal to s squared for inversion in a sphere. The only difference is that the image in the cylinder is the same magnitude but opposite sign to the original charge. Okay. If we repeat the solution with v replaced by minus v, we get the mirror image of the circle on the right by reflecting with respect to the yz plane as a mirror. Thus, we have a solution to the parallel wire transmission line formed by two cylindrical wires of radius r each and separated by 2h between their axes. One is at a potential minus v, the other is at a potential plus v, so the total potential difference is 2v, and you can use this to calculate the capacitance between the two cylinders, which is the capacitance per unit length of a parallel wire line. Okay, you can do this. And that ends the lecture and the end of chapter 6 on boundary value problems.